Here's a fluid mechanics question that looks at mass conservation, and there's also a bit of SUVAT at some point, as you'll see in a couple of moments. Now, this is the kind of question that usually first year engineering students who are doing some form of fluid mechanics might come across. And if you'd like to see anything similar to this in the future, or if you have any suggestions for any topics or specific problems related to maths, physics, engineering, and so on, let me know. So in this question, we're dealing with what we are given as a long cylindrical tube, and this is fitted into a hole made at the center of a thin disk of radius r. Okay, so this is just a 2D sketch, but actually the problem is three-dimensional, because what's actually going on is that if I try to draw this using an isometric view, then we've got something like this, right? So we have um, a pipe that is feeding water into this sort of sprinkler, and then we have the water coming out. Now, the drawing this sketch just shows the water coming out left and right, but actually the water is coming out radially, okay? Something like that. So this is either a sprinkler or something that you might see at water parks, for instance. And what we're asked to do is, as the water comes out, it will fall something like this. And the question is, what is the radius? Like this. So what is this radius of the water dome, basically, for a given depth h? Okay, so h is, let's say, the distance from the top all the way to wherever I'm trying to measure the radius. Okay, so the first thing I would do is actually rename this variable here mu, okay, which is the mass flow rate. So instead of this, I will write m dot. Okay, and this is the same mass flow rate, but I think m dot is a bit more common, so we're going to use that instead. So we know the mass flow rate that goes into the main pipe, and then we're trying to find what is the expression for the mass flow rate coming out of that sprinkler at the top, right? So this sprinkler, if I zoom in a bit, you'll see that this actually has a cylindrical shape, okay? And the water comes out in all directions from this surface or lateral surface of the cylinder. Okay, so we have to find an expression for that lateral area of the cylinder, and that's quite easy to do. So the lateral area of the cylinder is given by the circumference of the circle, which is 2 pi r. Right? We know this radius here is r, which means that maybe I should use capital R for this radius. And then this is multiplied by the thickness or the height of the cylinder that we know as h, like that. Okay, so the first thing I would try to do is find the velocity of the emerging water jet. Okay, so we know that the mass flow rate is conserved, so the mass flow rate is equal to density multiplied by 2 pi r times h times u, okay, where u, by the way, is this velocity here at the top. So if we actually rearrange this, we should find that u is equal to m dot over 2 pi rh, or rather over rho times 2 pi r and then h, like that. Okay, so that's the expression for u. And what we have to do now is find what is the radius of the water dome at a certain depth h. Okay, and to do that, we're going to use the SUVAT equations. So I'm going to model my object as sort of a water particle, right, which comes out of the sprinkler with a velocity u, and this is what we have. So let me try to pick a suitable coordinate system here. So this is my coordinate system. I will use x this way and y going downwards as positive, and this is my depth h. Okay, so I want to find out what horizontal distance that water particle travels by the time it travels a distance h, by the time it travels a distance h vertically. Okay, so this is u, and we've got this parabolic trajectory that we know is the case with free fall, right? So this is what we know. We have h equals, now there's no initial vertical speed, okay, so that's just 0 plus 1/2, and then we have g, and then we have t squared, which means that t squared is 2h over g, which means that, of course, t is the square root of 2h over g. Now, this tells us that the time it takes for the particle to travel from here to here is this, okay? And then we have to find, okay, so in this time, how much does the water particle travel horizontally, okay? And we know that the horizontal speed is u, so the distance is going to be equal to the velocity to u times the time, which is m dot divided by rho, and then we have 2 pi r h multiplied by square root of 2h over g. Okay? Note that this h, the capital H and the lowercase h, they're different things, right? This one is the height of that cylinder, and h is the depth where I'm measuring the radius. Okay, and that's pretty much it. Now we have to do one more thing, because this gives us this distance, right? This horizontal distance, but we're trying to find the radius of the water dome. So for that, we also have to include small r. Okay, so small r plus that gives us the radius of the water dome. So that's r plus, and then we add up m dot over, and then we have rho times 2 pi r times h times the square root of 2h over g. And this gives you what the radius is as a function of the height or the depth where you're measuring it. And as you can see, it's there's a square root relationship between the two of them, and you also have this constant added at the front. And that's the end of the question.